stress it. Want to show you guys on what is inside. We have cope, we have drag. So this is a mold cavity. This is mold cavity. This is open riser. This vent, right? So this is blended riser, and this pouring basin. This molten this metal is poured here, and so this molten metal, liquid metal, and will go because of this is a gravity, and go to the cavities that this it can reaches. So then after some time, right? After some time, the cooling, the solidifies after the solidification process finishes, and then you can just open and these two halves, upper one and lower one, and to get, and this is get the product. So here is the sand. Do you guys know why we use the sand here? Can somebody tell me why? So sand is the chemical name is what? Silicon oxide, right?
Is it because when you pour molten metal in the sand in the mold, that the sand will maintain its structure, and that your mold will keep its shape?
Who is speaking?
This is Reed.
Yeah, that's awesome. Because the sand, silicon oxide, it has very awesome, very high melting temperature. It will not be affected, and by this is the molten metal. That's very great point. So fluidity consists of two basic factors. So the characteristic of the molten metal, because molten metal plays an important role, this guy will go down because of gravity and reaches, this guy will reach the cavities that and it can reach. So this is molten metal is very important. Characteristics of molten metal is very important. Second one is the casting parameters. So here are the following characteristics of molten metal influence fluidity. So how is the fluid? The first one is viscosity. It depends on this inherent property for this metal. The fluidity decreases as viscosity and the viscosity index increases because it's very viscous. That can be a problem. And surface tension. So here is the surface tension. A high surface tension of the liquid metal and reduces fluidity. So if the surface tension is very high, oxide film, because of high temperature and because of high temperature, when it solidifies, you will have some oxide. This is the films, and developed on the surface of molten melt and have a significant adverse effect on fluidity. Oxide film, and will affect the fluidity substantially. And for example, oxide film on the surface of pure molten aluminum triples the surface tension. There's a tension. Tension means that it will not flow freely. Inclusions. As soluble particles, so inclusion can have a significant adverse effect on fluidity, and this effect can be verified by observing the viscosity of liquid such as oil with and without fine and sand particle in it. So this is very obvious. It will be noted that the former will have lower viscosity. This is inclusion. And another one is solidification pattern of the alloy. So this the manner in which solidification occurs, as described in this section, can influence fluidity. Moreover, fluidity is inversely proportional and to the freezing range. Right? Thus, the shorter the range, and the higher the fluidity becomes. So I might ask you guys, what are these factors that affect fluidity? And you can just show me these. That'll be good enough.
Can you re-explain inclusion, please?
Pardon me?
Can you explain inclusion again, please?
Inclusion?
Yeah, I didn't get inclusion.
Inclusion is some insoluble particles and in the fluid. So inclusion can have a significant adverse impact on fluidity. Fluidity means, hey, Reid, you have very, very nice mask, Reid.
Thank you, Professor.
So if there's multiple the particles within this fluid, definitely this fluid will not flow as fluently as it does without any inclusion.
There's just like little bits in it.
Yes, lower the speed of flowing.
Okay.
So like a practical example of that would be like if sand from the mold got into the molten metal, that would reduce the fluidity.
That's a good question. Yes, theoretically it is.
Okay.
Theoretically it is. You're right. So the following casting parameters influence fluidity and also influence the fluid flow and thermal characteristic of the system. Mold design, right? Design and the dimension of the components such as a sprue, runner, radars, all influence fluidity to varying degrees. Mold design, mold material, and its surface characteristic, and this one determines the cooling rate, right? So degree of superheat, and do you know what a superheat is, guys? A superheat defined as the increment of temperature above alloy's melting temperature, melting point. If this is melting point is 1000 degrees C, I just give you an example. So the superheat is that I just increase, the temperature is 1200 or 1500. So degree superheat. The 150, 1500 is has higher degree of superheat, right? So this is a rate of pouring, and how quickly you pour the rate. So heat transfer, the viscosity of liquid hence is a heat transfer. Okay, heat transfer affects the viscosity of the liquid metal, hence is fluidity.
The higher heat transfer, the more fluidity, or the opposite?
What?
Is it the higher heat transfer, the more fluidity, or the lower heat transfer, the more fluidity?
So the heat transfer is very quicker. So that means that this fluid can become solidifies quickly. So the more higher heat transfer rate and lower fluidity.
Okay, thank you.
So there is a castability. So we have machinability. Machinability is used to characterize how difficult it is to machine a workpiece. So here is a castability. So how easy it is to cast this material. So describe the ease with which a metal can be cast to obtain a part with good quality. It is a castability. Is very, very awesome word. And then we talk about temperature distribution within a mold. So this is air, this is surrounding air, and so this is a mold, right? So within this mold, we have this molten fluid. The molten fluid, we have two parts. One is liquid, one is solid. Solid is a solidifies the liquid, solidifies much quicker. The reason is that, and this part is near this mold. If it's near mold, that means the cooling rate is much higher than the cooling rate we have here. So this is the reason why this part and we get a solid material quickly, much more quickly. So here, so this is a room temperature in the air. So this is the temperature. This is a mold air interface. This might have delta T, right? Then here we'll have heat transfer, and here is a temperature difference. And within this is a mold, within this mold, and so the temperature and going up. Here is the interior temperature, and here is melting metal temperature. So here is a difference, temperature difference here, and the heat transfer will happen here and here because of This is the temperature difference.
So it goes from air to mold to solid.
Yes, mold here because the heat transfer is we have heat transfer here, so the cooling rate will be higher, right? And heat
the
transfer cooling rate
All right.
will be cooled quickly. The rate of cooling rate will be higher. So we have a solid here first, and then liquid, and this is solid that goes from this wall and to the interior part.
Okay.
And so this solidification time. So here is a Chorino's rule. This is Chorino's rule, solidification time, and C equals C multiplied by volume and surface area, and this is power n. So this is the rule, this Pico rule. And this how accurate this rule is, it depends on what kind of material you are using. So C is dependent upon this material. So as I said, this is a empirical, the rule, the formula, the equation. So if you want to get accurate this solidification time, and you need to use do the experiments, and you need to use validated this FEM model to predict the solidification time. Right? That's another story.
Professor, I just had a question.
Mm-hmm.
So, like, are we gonna have these equations on the test or
No.
no? Okay.
No. If you want, let me know.
Yeah, no thanks.
I'm not interested. As I said, for these parts, I just want to know to let you guys know some sketch ideas. But for the machining, a lot of details. Right? If I go very deep for this part also, and I think you guys will be very, very frustrated. But we only have one semester and 15 weeks. We cannot cover everything in detail. But it is good to know this is a sketch ideas. Right?
Real quick, what does C and N stand for?
And C is a constant. You need to check the table.
Okay.
The shrinkage during the metal casting process, we will experience the shrinkage. The shrinkage in a casting causes dimensional change. If the shrinkage is very, very big, and we will have substantial dimensional change, and which is very bad. Okay, and sometimes cracking, and is a result of following phenomena. And first one, contraction of molten metal as it cools before it begins to solidify. Okay, so this is a kind of contraction. And second one is the contraction of metal during phase change from liquid to solid. So this is the latent heat of fusion. So suppose the density is different, right? Density is different, definitely the mass is constant. If the density for these two phases are different, and definitely volume changes. The contraction of the solidified metal as the temperature drops to the ambient temperature. So this is from the solid at high temperature to low temperature. So this will have a shrinkage. So the largest amount of shrinkage occur during cooling of the casting. So metals, here is these metals during solidification and cooling. However, some metals expand, including green, the casting iron. So green casting iron is kind of the unique one. You should know that, okay? So shrinkage, I might ask you guys, give me example which expands during the casting. And you just show me the cast iron. Why? The reason is that graphite has a relatively high specific volume, and when it precipitates as graphite flakes during solidification, it causes a net expansion of the metal. So this is the reason. If I ask you guys, can you tell me any of these materials will expand during this solidification, and you should be able to tell me the green cast iron is one good example, and then tell me the reason, right? So most other metals, and they shrink during the solidification, but the green cast iron is opposite. Just like water, all the materials it contracts when the temperature becomes lower, but water is opposite. Well, water is unique. Water expands if the temperature goes down. So melting surface. Commonly used are electrical arc, induction, crucible, and caprolite. This is melting surface. Well, we have melting surface there, melting furnaces. And we have the metal, this metal usually the raw material, and they are solid. And first, we want to get molten metal. How to do that? Elevated temperature. And how to elevate the temperature? Using furnaces. And we have a furnace downstairs. That's a very good one. So you should know this. We have these 4 commonly used furnaces there. I will not raise this detail. You can just take a look. If you see these questions in either the quiz or the exam, you should be able to come here to tell people electrical arc, induction, crucible, and caprolite. Then this talk about custom material properties. So you can, I'm sorry, I need to tilt my head. So it's kind of painful, right? So automated tensile strength, this is modulus of elasticity. This is tensile strength, the density to density ratio. This is yield strength. You can see the different materials, they have different, and this is the properties. You can select, this is a property of material, and based on these properties, right? So I will not test your understanding. However, if there's a need later and to select what kind of material you want to cast, and you should be able to using these 4 figures to select one. So here is perennial harness, this elongation, this reduction of stress, reduction of area, I'm sorry. This is impact energy. And you can just look at this is the materials. The general characteristics of casting. For this casting, the typical material casting is a sand, shell, evaporative pattern, plastomer, investment, permanent mold, die, conjugal. So these you need to look at your textbook, right? We have this casting there. So weight, shape, DC shape of complexity, dimensional accuracy. So all these things you can just take a look. Right? So you have different casting techniques. You just take a look. This is too many details. I cannot test your understanding of this. You also know that all the quizzes and all the exams, they are take home, right? So typical applications and the characteristics. Type of alloy, so aluminum, copper, gray iron, magnesium, this is a malleable iron, nickel, nodular iron, and steel and white iron, and zinc. So here, and they have these different applications here. So this is castability. So this is weldability, and this is machinability. So E is excellent, and G is good, F is fair, VP is very poor, and D is difficult. And you can see this aluminum aluminum castability is very good. We know that, right? Aluminum alloy, and actually this is from very long time ago. The human ancestors, they use aluminum. So properties and applications of cast iron, and cast iron is useful also. There are several different cast iron. We have green cast iron, ductile is also called nodular, and this malleable white cast iron. So this is a type, right? This is a ferritic, pelitic, martensitic. So this is ferritic, pelitic, tempered martensite. This is ferritic, tempered, and this is pelitic. So this ultimate tensile strength, yield strength, along with their elongation in 50 millimeter. So these are typical applications. So these are cast iron, and I think in the material science, and you will learn and how many different cast irons we have. So we have these 4. Okay, I might ask you guys to tell me how many cast irons we have: green, and ductile, malleable, and white. Then talk about this non-ferrous alloy. Non-ferrous alloy means that, and these alloys do not have iron. So that's called non-ferrous. For this non-ferrous alloy, aluminum, so you can see aluminum alloy, and they are commonly used one. Magnesium is very awesome. Magnesium is very awesome element, and copper and zinc. And so this is the condition, right? Casting method, ultimate strength, yield strength, elongation, along with the hardness. So this is the hardness. So this is for commonly used non-ferrous alloys. So then we talk about this microstructure for cast iron. You might know that the cast iron is very good material for lubrication or for damping, right? To reduce the damping. And why? And after we talk about this microstructure for cast iron, you will know, because we have graphite there. So for this one, ferritic green iron with a graphite flakes is graphite flakes. For this one, and ferritic nodular iron is nodular iron. The ductile iron with graphite in nodular form, this is graphite. This one, the ferritic malleable iron, and this cast iron more solidifies as white cast iron, and with the carbon presence as this cementite. Cementite is an intermetallic material, Fe3C, and was heat treated to graphitize the carbon. So this is the 3. Ferritic green iron, and ferritic nodular iron, and this is the ferritic malleable iron. So this is the property of the casting alloy, or the die casting alloy. So, and we have aluminum 380, aluminum 13, and brass, magnesium, zinc, and zinc. Ultimate strengths are given here, yield strength, elongation, along with their various applications, which are given here. So heat treatment. So they are commonly used heat treatment for non-ferrous alloys and stainless steel. The last time I talked about phase change, this diagram, phase change diagram, that is for the iron carbide phase change diagram. That is the most important diagram when you learn the material science for the iron, okay? But here we talk about the commonly used heat treating for this is non-ferrous alloys and stainless steel. One is a solution treatment. The alloy is heated to or within this solid solution phase. and cooled rapidly. So this is solution treatment. And another one is a precipitation hardening and put these particles inside. So the third one is artificial aging. And you after you finish the casting this non-ferrous alloy, just put in the room temperature and stay for several weeks until you have artificial aging. Here is a phase diagram for aluminum copper. So as I said last time, I told you guys this diagram, phase diagram, and we have this abscissor. Abscissor is usually the content of the material, and the ordinate is the temperature. We can see aluminum, copper. So here is a pure aluminum, and this one is a pure copper. And for other concentration are located in between. Here is a liquidus line, and here is this is a K. K is a phase, K plus liquid. So here is the solid. For any given concentration content, and you can draw a vertical line to know how the phase changes as this is the temperature increases or decreases. So look at here, okay? So this X, this is a solid solution, and X, this solid solution, XA quenched, and solid solution retained, and this is A and B, H hardened, precipitation starts, this is precipitation, AC overaging, precipitation agglomerates, this is a precipitation. You can see that these the particles, they are the precipitation. So outline of heat treating. So carburizing, carbon nitriding, this is cyaniding, nitriding, boronizing, flame, this is hardening, and introduction, this hardening. So these are different processes. You can have material hardened, element added to surfaces, and also procedure how to carry out these the heat treating processes and general characteristics, and also this is the typical applications. This is a lot of information. I cannot test your understanding of everything. So cost processing comparison. So there's a different processes. So here's advantages and limitations, and you can just take a look. Okay, stand. My bottom line is you know the stand. What is the shell model?